Hello, everybody. My name is Nevin Brocious. I'm a PhD student in chemical engineering at University of Florida. I'll be talking today about surface tension measurement using a resonant forcing technique of levitated metal droplets. So this is a collaborative effort between the Japan Aerospace Exploration Agency and NASA Marshall, as well as UF. You might be wondering, what is the importance of thermophysical property measurement? How does that translate to operations on Earth and industry production? So these levitation-based technologies can provide a measurement level accuracy beyond which is typically possible with other containered methods because you don't have the contamination effect. So we can study these kind of fundamental behaviors of levitated metals, glasses, and oxides to translate directly to very important engineering processes, including modeling of very important processes and material development. So studying alloy behavior that will be translated to a turbine blade design, for example. So there's several levitation facilities that exist. One is the ELF at JAXA. There is one on Earth and on the International Space Station on the Kibo module. There's also the electromagnetic levitator on the Columbus module on the ISS. And then there's the Kibo, which is the one on the ISS, and the ESL at NASA Marshall, that's in Alabama. And that's where most of the experiments shown in this work have been conducted. The way that a metal sample is electrostatically levitated was very well described by a colleague as being similar to the process by which your hair stands up when it's charged with static electricity. So we charge a metal droplet with photons using a laser, usually a UV laser, to incite surface charge. And then this electrode system is used to levitate the droplet using a control system. And so what we do once we get the actual metal droplet levitated is we then melt it and superimpose an oscillatory electric field over the levitation electric field. So below what we call the resonant frequency for this liquid droplet, we just get solid body motion. And so it just oscillates up and down like a spheroid. But as you approach the first natural frequency of the sample, it begins to undulate in a very predictable fashion. And it is this frequency at which that occurs that correlates directly to key thermophysical properties that are very important to measure. So this was actually determined analytically back in the 1800s by Lord Rayleigh as corresponding directly to the surface tension and the mass of the droplet. And of course, there's a lot of assumptions that come into this. This is the formula for an inviscid sphere. So in the limit of low viscosity, perfectly spherical, there's no electric field effects. And of course, in reality, a real system doesn't have infinitely small error with that kind of measurement. However, the experiments that we've run show that, in essence, the system does behave virtually inviscid, virtually as a sphere. And so this formula shown here is remarkably simple, and it's very powerful. So the N corresponds to the normal mode at which the sample oscillates. So this is a spherical harmonic, and it just goes 2, 3, up to infinity. Here's a video of n equals 2. It's an oblate prolate shape. So as you go around the sphere in the polar angle, you have 2 waves. And then the n equals 3 is shown on the right. That has 3 waves in the theta direction. And m is, of course, the mass, and gamma in this equation is the surface tension. So you can see as surface tension increases, the frequency increases. As the mass decreases, the frequency increases. Fairly straightforward. So this technology, or this theory, has been used to measure surface tension for the past few decades, actually, since the 90s. And so what they would do is they would pulse the droplet and let it come to rest naturally. And the natural frequency, which would be plugged into the previous equation, was in the limit of long oscillations. You would essentially get a low amplitude oscillation, and the frequency would approach that of the natural frequency, which is in the equation on the previous slide. So they would do an FFT, analyze it, and figure out what the frequency was. Then you could back out the surface tension. So our technique involves resonant forcing. So the advantage of using resonant forcing is that we avoid any kind of control system. When we do a pulse, you have to keep in mind that there's a control system that is operating on that sample. And so when you let go of a pulse, the control system will inevitably cause changes in the droplet's behavior. Also, we allow for viscous samples. So if on the previous slide, you notice that the pulse was able to oscillate several times before finally coming to rest. But with viscous samples, that's not really quite possible. And so what we do is we continuously force the droplet. So viscosity never comes into the picture in terms of the actual droplet response. And so here we have an experiment where we've levitated a zirconium droplet and then recorded the deformation, known here as the normalized maximum diameter of the droplet, as a function of the forcing frequency that we superimposed over the electric field. And so you can see that at 185 hertz, there's a strong resonant response. And this corresponds to the resonant frequency of this zirconium sample, and we can back out the surface tension from that result. Now, we are slated for ISS experimentation next year. And so we wanted to do this experiment on the JAXA equipment because it's essentially a clone of the same device that is on the space station. And so the way it works is a laser shines a light over the sample, and the shadow is collected. The data representing the shadow is collected on the sensor, and you can get what is essentially the area of the shadow as a function of time. So this is a sweep, a frequency sweep, we call it, to get the response as a function of forcing frequency. So here's at 247, 256, and 262 hertz. You can see there's a strong increase and then decrease. We call that a resonance curve. And here again, we find the resonant frequency. We can back out the surface tension from this data. So we also wanted to see how we could quantify the surface tension in a sample, also using one of the higher order modes. So a lot of work has been focused primarily on mode 2 because it's considered the fundamental mode. So as you let the droplet decay over a long period of time, it will eventually oscillate in that fundamental mode, the mode with the lowest energy. Now, using this Japanese setup with the shadow, we showed that the area change with the same amplitude of this normal mode is pretty much unsensible in mode 3. So you can use this technique, you can use this shadow technique to identify mode 2, but not mode 3, because it does not, the shadow area does not change significantly. So here's a little animation demonstrating that. As mode 2 changes, the area changes quite a bit, and as mode 3 changes, it does not change the shadow area significantly. We have to back up a little bit before we attempt to quantify the shape of the sphere. So we have to understand that oscillating droplets in the theory that was described or shown, that theoretical result from Rayleigh, he assumed that the oscillating droplets go as the spherical harmonics superimposed onto a sphere. And for image analysis purposes, we assume that it's axisymmetric, so we're only using the axisymmetric form of each mode. And so that simplifies the equation a little bit. And so here's what the second Legendre polynomial looks like. That's the mode 2. And this is mode 3. You have the 3 nodes in the theta direction. So we had to come up with a way to take this video data and quantify how strong is this sample oscillating as a result of our forcing frequency. So the basic procedure that we use is we take the frame of the video while it's oscillating, we convert that into an outline and subsequently into polar coordinates. Then we perform a numerical integration to find the essentially the magnitude of that particular mode, so in this case mode 2, and we plot that as a function of the forcing frequency for each video. So each of these data points represent a specific video of the experiment. So at each video is a constant forcing frequency, and we can see that as we increase the forcing frequency, we get a rise and then a subsequent decline, and the maximum is our resonant frequency. We can then back out the surface tension this way. Now this translates fairly straightforward to mode 3. We take the droplet frame that we get from the high-speed video. We then outline it using image analysis and then convert that into polar coordinates, perform the basically the same numerical integration, but you can see here that we're taking the projection onto the third Legendre polynomial because it's mode 3. And then we plot this as a function of the forcing frequency. We can find that it has a similar max. We plot that as a function of forcing frequency, and we can back out the surface tension in the same way. We use this mode 2, mode 3 kind of check as a way to benchmark the measurement of the mode 2 experiment. So say, for example, we got 1.5 newtons per meter from the mode 2 sweep. So we found the resonant point in mode 2, and we're able to back out that value of surface tension. We can then use the same sample at a different frequency range and confirm that the surface tension is approximately 1.5 newtons per meter, for example. So in summary, resonance can be used to measure the surface tension in levitated liquid droplets. The area array that will be used in on the space station and is in JAXA can be used to quantify even modes, but not odd modes, as shown in mode 3. Odd modes can be characterized with high-speed video. So in the future, in this future experiment where we will be looking at higher order modes, we will be characterizing mode 4, which has not been observed, but we expect to observe it soon using the area array, the shadow technique. So I'd like to acknowledge JAXA and NASA Marshall, as well as NASA for funding and the Florida Space Grant Consortium, in addition to the UFIC Research Abroad for Doctoral Students Award, which funded travel to Japan to do some of this work. And of course, one of these is my NASA Space Technology Research Fellowship, and I'm very grateful for NASA's support on this